Welcome to the Anomaly Detection and Covert Channels track. It's a scientific track. Today, in this section, we have 5 papers. As usual, if you have any question, please write on Slack or on the QA chat session, because then I will select some questions for the speakers, and we can start with the first speaker, that is Serena Ferracci, that will be presenting her paper on detecting phishing emails using text mining and features analysis. So Serena will be enabled to talk about the video. I think the host will start the video, the slides.
Okay.
Okay, 15 minutes, please go ahead.
Okay, thank you. So, good morning. My name is Serena Ferracci. I'm a cybersecurity researcher for Hermes Bay, and I'm going to present detecting phishing email using text mining and feature analysis. The presentation is divided in a brief introduction about the phishing attack. Then we have the state of the art. We summarize the most common solution proposed so far with advantages and disadvantages. Then we have our methodology, how we analyze the email, and finally the result, how we construct our dataset and the tests we have done. First of all, what is a phishing attack? They use phishing email that are particular email that look like real legitimate email used by malicious actor to trick the victim in order to steal them sensitive information, for example, bank account information, using a link to an external website that look like a real website, but is a fake one, or to infect the PC of the victim using a malware as an attachment of the email. The solution proposed so far for this attack can be divided into 3 main areas: blacklist, heuristics, and data mining. The first one is blacklist, the simplest and lightest one. It is a list of detected phishing URL, IP address of keyword. It provides protection against attacks that are already seen, but not against zero-day phishing attack. Then we have heuristic, that is a collection of the characteristics that are found in real phishing email. It's more complex than blacklist, but it can be possible to detect also zero-day attack. And finally, we have data mining that exploit machine learning technique to clustering or classify incoming email. They also use they also choose characteristics in order to analyze an email, but we have also need to build a dataset labeled so suitable for the analysis. So a good balance between efficiency and effectiveness is heuristic. And let's have a look of what are the main methodology. They are based on heuristics. In the literature, there are many examples for, and there are network analysis. They use the characteristic derived for the network, for example, the IP address source and other to classify the email. Then we have website analysis. In most of the email, we have a link to a fake website to steal information from the victim. And they use the URL and the destination web characteristic to understand the nature of the email. And then we have text analysis. The methodology is based only on the text contained into the email. We decide to extend text analysis because we want to use only the data available in the client side in our email. For our email, we intend the HTML format email that is not already processed. So we have two categories of information, the metadata and the text. Starting from the metadata, we extract the relevant feature, for example, the from field, or if there is an attachment or not, and we assign to each characteristic a score. Higher the score, more dangerous is the email. Then from the text, we build a vocabulary starting from a phishing email corpus. This vocabulary is a sort of word used in a phishing email. The vocabulary is sorted in accordance to the frequency of this word. So how many elements in the corpus contain this word? And then we start the analysis of the text. We use both the body and the subject. We using the text mining analysis techniques, we process both body and subject, and then we check how many of the word of the body and the subject are present in the vocabulary. To each of these words, we assign a score. If the word is in the first position of the vocabulary, they have a greater score. And if there is the word is in the latest part of the vocabulary, you will get a lower score. The score then is normalized and is summed with the previous one to get a total score. The score will be between 0 and 10. Then we choose a threshold. Above this threshold, if the score is above this threshold, we classify the email as a malicious one or suspicious. Below this threshold, the email is considered legitimate. But let's have a look at what we present to the user. We do not present a binary result, only suspicious or legitimate, but we present all the characteristics we analyze, highlighting the suspicious one. In particular, we have green for the characteristics that does not present a danger for that email. In yellow, the suspicious one, and in red, the one that are typically of a phishing email. In this example, even without looking to the score, we can see that the first one is a legitimate email and the second one is a phishing email. So we can think that we can assign a uniform score to each characteristic in order to obtain the correct classification. For example, assign 1 if the characteristic is suspicious, 0 otherwise. But what happens if we have a situation like this? Using a uniform score, we will wrongly classify both email as a legitimate one or a phishing one. That's because some characteristics are more dangerous than others. For example, the presence of an attachment will be more dangerous than a subject that presents word common in a phishing email. So we decide to use heterogeneous score in accordance to the report presented by major companies like Google, Aruba, and Apple that listed and sort the most common and dangerous characteristics for the email. And using this score, we can correctly classify the first one as a legitimate email and the second one as a phishing email. The results obtained with our research are to obtain a realistic dataset. Most of the solutions proposed so far use a 50-50 dataset, 50% of phishing email and 50% of legitimate email. The dataset are proposed by detected phishing email using text and data mining and evolving fuzzy neural network for phishing email about 50-50. But this not represent a realistic scenario because a victim does not receive so many phishing email with respect to the realistic one. So we decide to use a dataset that is composed by the 90% of legitimate email and 10% of phishing email. And we have done all the tests using this dataset. Like we see, we does not present all the result phishing, non-phishing to the user. We present all the characteristics using 3 labels. Not suspicious, suspicious is phishing. So the color green, yellow, and red. This is done to educate the user in order that he can also understand why an email is classified as phishing or a legitimate one. And finally, we achieve a 99.2% of accuracy. We also think about some future work, both from the research standpoint and also for the presentation. Since this classification is quite efficient, we can also think to use this as a layer or a pre-filter for a more detailed analysis. For example, an analysis that take into account the attachment and linked website. So an analysis that can involve also a sandbox, so test the attachment in a sandbox, use the result. And then for the graphic, we would like to present to the user not only the statistics. So we have found 3 words that are most common in phishing, but we would like to present to the user the whole email and the whole metadata, highlighting the particular word, the particular characteristic in the metadata that lead us to classify the email as a phishing one or a malicious one for educate the user. So thank you all for the attention. If there are any questions, I will be glad to respond.
Thank you, Serena. I'm looking at Slack, but I didn't see any question, not even in the question answer. I have a quick one because you run a bit late. So did you consider if, because you need to build a model and then you apply the model, did you consider if the model change over time, and did you test how often the model, if the model change, and how often that will change?
So we can yes, we can adjust the model through the time. For example, the vocabulary can be recomputed adding a new phishing email, but the common word for the email shouldn't change so much over the time. And for the characteristic, like also the all the heuristics based methodology, we should add new characteristics to analyze for adapt the model to the new attacks.
Okay, thank you. Thanks for your presentation. We'll move to the next paper presented by Marco Zuppelli, so you can start his presentation. The paper is detecting covert channel through code augmentation, and say that Marco Zuppelli will be.
Hello. Yes, I'm not allowed to share my screen. Okay, thank you.
Okay, I will write on the chat when you are 2 minutes close to the time, but please go ahead.
So, good morning, everybody. My name is Marco Zuppelli, and I'm a second-year PhD student at the University of Genoa and a research fellow at the National Research Council of Italy. Today, I will present our work. So, nowadays, malware uses more frequently information hiding and steganography techniques in order to remain unnoticed from detection techniques. This novel class of threats is called stegomalware. Stegomalware enable to elude well-known detection techniques, exfiltrate sensitive data, covertly orchestrate an attack, and so more. So, among the multiple different techniques that can be adopted by an attacker, we investigated on the uses of covert channels. A covert channel, according to Lamson, is a channel that is not intended for information transfer at all. In other words, it is a hidden path that can be exploited by attackers to hide malicious communication into digital object or treatable carriers. There are three metrics that describe a covert channel that are detectability, steganographic bandwidth, and robustness. The metrics are linked to each other. In fact, it is not possible to achieve an high steganographic bandwidth without giving up on robustness or detectability. For example, if we want to put main information in a network packet, this packet can be more detectable by third-party tools and detection techniques. So in literature, there are two main types of covert channels that are local covert channels and network covert channels. An example of a threat that uses a local covert channel is the colluding application threat. In this threat, there are two entities that can be processes, virtual machine, or Docker containers that resides on the same host, but are separately with security permission by the host itself. And they find a way to secretly communicate. For example, they can do that manipulating the usage of the CPU or allocating some space on the disk. Instead, an example of threat that uses a network covert channel is exfiltration of sensitive data to a remote command and control infrastructure. In this case, the two network peers uses a legitimate flow, modify this flow and the packets that are within this flow in some way in order to transmit some information. This work is focused on the network covert channels based on IPv6 protocol. This is because IPv6 is becoming more popular and used by the community. So for this reason, it is important to anticipate IPv6 network covert channels. Many features of IPv6 can be exploited for the creation of covert channels. And there are many sophisticated techniques that can be adopted in the IPv6 protocol to conceal some information. In this work, we used three covert channels based on three different fields that are flow label, traffic class, and op limit. These fields are not always used in a proper manner and can be used to contain information without disrupting the normal behavior of the protocol. So there are many challenges in this sense because there is a vast range of steganography and information hiding techniques, along with a set of carriers that are heterogeneous and unbounded. This makes the detection hard. The detection of covert channel hard. Moreover, existing detection techniques are very specialized. For example, to inspect network packets or to perform some image analysis. So there is the need of a unique technology that can be extended in an easy manner and that can cover multiple covert channels at once. We identify this technology into a eBPF, or Extended Berkeley Packet Filter. That is a technology that can run programs into the Linux kernel without changing the kernel source code or loading kernel modules. eBPF is born with the idea to monitor and observe the Linux kernel. eBPF programs are event-driven, which means that when a certain hook point is passed by a kernel or an application, the programs are triggered. There are many predefined hooks, including system calls, kernel trace point, or network events. Typically, the programs are divided into two parts, the user space and the kernel space part, that can communicate through kernel maps, which are data structure like arrays or hash map. There are several development toolchains that assist the developers to manage eBPF programs. In our scenario, we use the BCC. That is a framework that enables the users to write Python programs into Python programs with eBPF programs embedded inside the lab. When we deal with network traffic, we should pay attention to something. For example, if the volume of traffic that we want to inspect is huge, we should take care of memory and disk usage in order to not have scalability or I/O performance problems. Moreover, it is necessary to pay attention to sensible information that, for example, some packets can contain, always looking at privacy and anonymization problems. For this reason, we thought about a data structure that can solve these problems. The idea is to split the whole range of flow label, traffic class, and the hop limit field into a smaller number of groups that we call beans, and use a counter for each group. This allows to map a larger space, for example, flow label that is a 20-bit field. So this allows to map a larger space into a smaller one, and for this reason we can save up some memory and disk space. For each incoming packet in the node that run the filter, the interested value, so flow label, traffic class, or hop limit, is placed into the corresponding bin, and the counter is incremented by 1. This allows us to roughly estimate, for example, the number of flows in the network or the number of packets. In the end, we are able to collect information of traffic through counters that make them available in a sort of array form. So it is easy to deal with the array. So we prepared our testbed, which is composed of 2 virtual machines that are able to communicate through a third virtual machine where the eBPF filter run. So at first, we wanted to investigate on clean traffic. The clean traffic was replayed via TCP reply, and it was gathered from, it is real traffic gathered from CAIDA. And we investigated on the number of bins changed between 2 subsequent sampling intervals. The sampling interval was set to 1 second. The number of bins was set to 2 to the power of 15 for flow label and 2 to the power of 8 for traffic class and hop limit. Moreover, the covert communication was set up using Hyper-free tool, and by using an ad hoc Python script, we were able to modify this traffic and make a covert channel possible. So here are the results. As you can see, our metric can characterize in some sense the network traffic. In this case, we plotted the behavior of the free fields during 15 minutes of network activity of clean traffic, so traffic without any covert channels. As you can see, for the traffic class and the hop limit, traffic class and hop limit are characterized by a few values observed. So while the flow label has more flexibility and variance. So for example, when an attacker wants to use a covert channel based on traffic class, he can disrupt significantly the normal behavior of the rest of the traffic, and for this reason being detectable. For this reason, we try to make a covert communication using traffic class and a secret of 1024 bits. In this case, our metric is able to easily spot the channel because it is clear that in some part of the communication the spikes are so much different from the rest of the other spikes and from the rest of normal behavior. So what an attacker can do, he can choose to tune its channel at the expense of steganographic bandwidth. So in the second chart, you can see how our matrix varies according to a different steganographic bandwidth. So the communication lasts longer, and the spikes are more close to the normal behavior of the traffic. In conclusion, we proposed an ABPF-based code augmentation approach, which can efficiently collect data. We are able to monitor different fields with minimal adjustment. And obviously, our future works aim at develop a metric that is able to spot the presence of network covert channels. And we want to automatize the process, the detection process through machine learning techniques, also considering different network covert channels and network conditions. Actually, we are searching for some threat-independent metrics which are able to detect both local and covert channels. So thank you. If you have any question, please let me know.
Thank you, Tommaso, for your presentation. No, not Tommaso, sorry, Marco, for your presentation. Don't see also question in the Q&A and not even on the Slack. So I have a question for you. One is, what is the impact in terms of performance of doing all this filtering? It's one question. And the second is, of course, any network protocol is subject to the kind of covert channel you mentioned, because any network protocol has, for example, unused bit, and you can exploit them for covert channel. Now, what you presented work if I put in the header of IP version 6, but if the attacker simply moves and do the same trick on this TCP packet, well, you don't see anything.
The advantage of this of our approach is that this data structure that we thought can be is flexible. So if we want to check another fields of another protocol, we can do that without so many changes in the code. So this is the reason why we thought. Yes, theoretically, yes, we plan to extend this work to other network. Okay,
I understand. But okay. The first question was not unrelated, because of course you can do deep inspection, but if you do deep inspection at every level of encapsulation, it takes time. So what is the performance? Then it became that's why at firewall level you don't do deep inspection, because then you delay too much the traffic. So that's why the impact in performance.
We measure also the impact in terms of performance and in delays of network packets, and the delays are not significant, because the ABPF program is triggered only when a packet passes through the network. So this is one thing. The other thing is that we measure the usage of the memory and the usage of the CPU. Unfortunately, the usage of the CPU is not a straightforward forward operation to measure. But in terms of memory, we find out that for a traffic class and hope limit, since they are short fields, we measure 3% of the usage of memory and 12% in the case of flow labels. So I think that for a network, we think that for a network node, these measurements can be managed in a good manner.
Okay, thank you for your answer. And now it's the time of Tommaso Zoppi. So sorry for the mistake before. And Tommaso, that he will be the speaker, will present a work on spoofing detectability as a property of biometrics characteristics. So Tommaso, also for you, you have 15 minutes. Please go ahead when you're ready.
Okay, thanks a lot. I'm Tommaso Zoppi from University of Florence, and I'm here today to present a work that we carried out together with Resitec SRL, which is our industrial partner, who is based in Pontedera in Tuscany. And this work is about biometric characteristics, and in particular, we are introducing a property and the related machinery, which we called spoofing detectability. So jumping straight into the topic, we start by recapping about authentication. So what authentication is, essentially, is the process of verifying the identity claimed by or for a human entity. So what is this about? This is about using or providing some functionalities just to authorized users. So I don't want other people to access my bank account. So my bank is requiring a password and an additional device in which I get a one-time password that I have to put and I have to text on a different device to access my bank account. Now, this is a process about multi-factor authentication because I need to know something, which is my password, and I need to have something, which is my smartphone, or it could be a different device. Instead, there is a third way of processing authentication, which is something which is based about what the user is. And this is important because essentially what the user is not something that can be forgotten, and it's not something that can be stolen. So essentially, I may forget my password, I may lose my smartphone, but I cannot lose my fingerprint, or I cannot lose my face, even if there could be some events that may damage this biometric trait. So in the last, say, 20 years, research moved a lot on using biometric traits as a way to authenticate people to some platform. And these biometric traits were classified according to different characteristics, such as universality, distinctiveness, permanence, collectability, performance, acceptability, and circumvention. Those were put in some tabular surveys, for example, this one, in which we see essentially on each row we have a biometric trait, and this biometric trait is matched with some low, medium, high bit value, which essentially specifies how this biometric trait fares with respect to each individual characteristic. Now, since we are interested in security, and authentication is closely related to security, we cannot avoid thinking about enemies, attackers, who may want to spoof, so conduct some sensor spoofing attack or presentation attack, which essentially aims at circumventing my authentication system, presenting a fake sample that the attacker forged according to some mechanism, and trying to get authenticated into a system, even if the attacker itself should not be authenticated to the system. And there are different examples. You can create some gummy finger, you can take a snapshot of my face and trying to authenticate on a system by using the snapshot of my face, and so on and so forth. There is one of the characteristics of biometric traits that we saw before, which is partially about this aspect, which is circumvention. Circumvention defines essentially how easy it is to forge, how easy it is to fool an authentication system which is based on a specific biometric trait. So it may be easy to generate, to take a snapshot of my face or to record my voice. It could be more difficult to have the same DNA trace or to have some other kind of biometric traits. However, this doesn't fully account for the overall cases that we may have when we think about attackers that may want to get into our system, even if they don't have the rights. Because even if an attack is very easy to conduct, or even if an attack is very difficult to conduct, so it has low circumvention, we have a different point of view that usually is a bit left out, which is about how easy it is to detect that there is an ongoing attack. So in our study, we claim that it's possible to use an additional, so it's possible to plan and to derive an additional characteristic of biometric traits, which we call spoofing detectability, which indicates essentially the easiness of understanding that there is an ongoing attack. This essentially pairs with the already existing biometric comparison system, because the biometric comparison is about reading a biometric sample and matching the biometric sample with one of the authorized users. Instead, we want in parallel to check if the biometric sample which is provided to the biometric comparison for authentication is legitimate or not. There could be some possible anomalies in the biometric samples that are provided to the authentication system. For example, if I have a gummy finger, it's the same finger across time. So I may, after seeing the exact same finger for different observations, I may start suspecting something. Or if the attacker reads, maybe steals from some channel or from some network the biometric sample, the attacker may try to add some noise in the background to, let's say, still be authenticated to the system, but every time provide a slightly different biometric sample, which is not the exact same of the one before. Then this noise may be so random that again makes us suspect something. So in this case, we claim that this spoofing detectability is something that should be paired when analyzing biometric traits, when choosing biometric traits to be used for authentication, should be paired with circumvention to have a very comprehensive view on the role of this spoofing detectability. So essentially what we want is having low circumvention, so a biometric trait is very difficult to forge, and high spoofing detectability, which is, it's very likely to detect an ongoing attack, which is the green area above this table. So what we did, essentially, we tried to estimate this spoofing detectability for different biometric traits. So we considered the fingerprint and gesture, face, voice, and we set up an experimental campaign about these traits. So we downloaded public data. Eventually, we extracted features from those data because those data is heterogeneous. Some comes as tabular data, some comes as images, videos, audio traces. So we use state-of-the-art machinery to extract features. So essentially, we have tabular data for all the biometric traits. So we pre-process the dataset and we get in a variant of this dataset, which is just tabular data. We build an attack model, a sensor spoofing model according to surveys. So literature study to devise an attack model that we can inject in our data. And this way we are getting datasets for each biometric trait, which are labeled. Either it's a benign sample, legitimate, or it's a spoofed sample that we created through injection of those attacks. Then we run some anomaly detection algorithms, unsupervised, and we measure their classification performance, which refers to detection of intrusions, according to the Matthews coefficient, which differently from accuracy, precision, recall, and F1 fits also unbalanced data sets. So when we have a lot of legitimate data and just a few attacks. So results are summarized in this table. We calculated the average Matthews coefficient score and the best Matthews coefficient score for each data set obtained by unsupervised algorithms. And essentially, we translated this number into low, medium, high classes, both for the average and for the best. And then at the end, we obtained what is here, the column in bold font, a value for the spoofing detectability, which we can, again, as we saw in the table before, pair with circumvention. So let's see an example. We have earth rate variability. In this case, I have medium spoofing detectability. So I'm likely but not sure to detect the ongoing attack, but this biometric trait has low circumvention. So this is quite a good biometric trait because it's difficult to trick, and I am likely to detect an ongoing attack. Instead, voice, again, I am likely to detect an attack, but it's very easy to forge. It's very easy to spoof voice because it has high circumvention. So this is me. We need to use this biometric trait carefully. As a last contribution of this study, we also tried to set up a runtime spoofing detection module on an already existing architecture about this ProtectID project. ProtectID project is a project of ResiliTech SRL company, which just ended. And essentially, it was about protecting digital identity of users that want to authenticate to online services. For example, Poste Italiane was involved in the project. So essentially, they already had their biometric authentication system with their biometric comparison. So we foresee essentially putting alongside and independently with the biometric comparison, we foresee the installation of an anomaly-based spoofing detection module, which essentially pairs with the biometric comparison and provides to the final decision. So we have a biometric comparison which tries to match the biometric sample to the authorized users, and the spoofing detection model which evaluates the legitimacy of that biometric sample. So to conclude and to wrap up, these works presented spoofing detectability, which is both a property, an additional characteristic of biometric traits, and a mechanism to be instantiated into an already existing biometric authentication system to strengthen some security properties. And this is something that can be plugged into an existing system because it's completely independent with the already existing biometric component. So you see here the main references of this presentation. For the others, please refer to the paper, and I am happy to take questions if you have time. Thanks a lot.
Thank you, Tommaso. This time I was right. So it seems that I'm the only one here doing questions, because also in your case, I don't see questions. We have a shy audience. Okay, so I have a question. So you talk about spoofing the detectability, right? And then your aim seems to be to see how biometric traits, if some biometric traits are more spoofable than other, no? Now spoofable, yes. I don't know the right word, but this is. But then why you tested on a single implementation? Because you know, when you have an implementation, spoofability, if you can spoof or not, depend on a zillion of parameters. For example, how you put the threshold, which kind of machine learning you use. If it's, okay, in this case is one class classification, but depend if it's always one class classification. It depends on a lot of parameters that have nothing to do with the traits. So the results you showed are results of the implementation and not results of the trait, related to the trait.
Okay, so this is okay. This is a very nice question, and in fact, we found it very, very difficult to have some kind of generalization which was completely independent with respect to the implementation. However, different biometric traits essentially are paired usually with different features that you can extract from the biometric sample. So from the fingerprint, you can derive different distances from essentially the edges of the finger. And essentially we found by looking at the data that there are some alterations of those features of the fingerprint, which essentially are usually specific for the fingerprint and not appear in the voice. So features extracted from the voice have a variability which is, for example, not a normal distribution, which is a different distribution. So in that case, we tried, again, to generalize a bit by using more algorithms, not just one, trying at least to not be specific to the one anomaly detection algorithm that we are using, and trying to have a study which is individual for each biometric trait by analyzing the alterations of specific features which are anomalous or which are, let's say, just noise.
Okay, yes, thank you very much.
Thanks a lot.
Okay, so we pass to next speaker. Sorry, but we have a tight schedule, so sometimes look like a bit rude, but it's just because we have a few time. So I think the next speaker is Ivan Vaccari, but my indication is that it will be a team presentation with Ivan Vaccari and Sara Narteni. I don't know if this is correct, but anyway, they will present, or he will present on the feasibility of Covert channel through SMS. So.
Okay, good morning. I will present our work.
Okay.
Can you see my screen?
Not yet, but we are working on that. Okay, you can go.
Okay, now. Okay. Good morning, everyone. My name is Sara Narteni, and I'm a research fellow at the National Research Country of Italy. And I'm going to present our work on the feasibility of covert channels through short message services. Covert channels and tunneling systems are between our research activities. And in the study, we introduce novel tunneling that is based on SMS messages. In computer science, actually, the tunneling systems are well established and are systems by which one can bypass the limitations of a network inside, for example, organizations. And it is done by encapsulating forbidden protocols into allowed ones. And this can lead to the exfiltration of very sensitive data and private. The typical scenario of application is that of the insider threat, where the insider is a member of an organization that wants to bring some private information outside. And it is still a current issue. In fact, recent news have reported about an Italian Navy member that has sold some private documents to Russian officials. And in general, the problem of data leakage is still current and can be achieved in many different forms, as demonstrated by another recent news of a big data breach from Facebook user data. In this work, we focus on the exploitation of mobile networks, and we wanted to assess the feasibility of a new tunneling system through short message service. A little bit of background about the SMSs. They are short text messages with up to 160 characters, and they are supported by the GSM architecture and also by a newer standard for mobile telephony. Here you can see our proposed architecture. In particular, we have developed two software modules. The first that is made up of a SOX and a tunnel client, with the SOX that is in direct communication with the client that can be, for example, a web browser, and the client can be even not connected to the web server. The other endpoint is the tunnel receiver that contains a tunnel server and a tunnel proxy, with the tunnel proxy that openly communicates with the web server. The internal parts of our system are in communication in form of SMSs. We have designed two kinds of SMSs. At the application level, such SMSs have a basic structure that comprises a header with the three fields, destination IP address and the destination port number, and the client port number that indicates a particular communication with the client. The index indicates instead the specific SMS, while the content is a fragment of a message that we want to transfer over the tunnel. To handle the communication at the transport level, we have introduced a special SMS that we call zero packet, and it has the index fixed to 0, while the content is either a 0 or a 1, and it is used to handle the connection between the client and the SOCs. Here you can see what we call the request pathway, and that is the data flow from the client to the web server. And the client performs a request. Such a message will be split into a series of SMSs by the tunnel client. Each SMS will then be sent to the tunnel server, and the tunnel server, after having received each SMS, will extract the content field from each of them, and each content will be then sent to the web service through the tunnel proxy. The opposite, once that the web server provides a response, such response will be sent back in a symmetric manner, and finally the response will reach the client. The main goal of our study was to assess if our tunnel is actually feasible in terms of the time delays introduced by the tunnel. And in order to study the feasibility of our proposed attack, we have developed some mathematics to assess such feasibility. And let's suppose that MR and MS are the request and response messages that we want to transfer over the tunnel. And we here focus on HTTP or HTTPS data, but they can be any kind of data actually. Such messages will be split into sequences of SMSs that we suppose to be of L characters with a corresponding byte size of SL. Now we can compute the number of SMSs that are required to send the original messages MR and MS, and we denote them with the KMR, KMS. The SMSs will be sent through the tunnel at a frequency of n SMSs per second, and now we are able to introduce the time delays to assess the feasibility of the tunnel. And let's denote TMR and TMS as the total amount of time to send the original messages, MR and MS. And in addition, we also must consider the timeouts of the client and the web server that are TC and TS. And they are useful because if they would be expired, there will be a connection closure. And also we introduce T alpha, that is the time needed by the web server to produce a response to a certain request. So to avoid any connection closure either by the client side or the server side, we have derived an equation that states what are the time requirements of our that must be followed by our tunnel. And you can see this equation in the bottom of this slide. So to avoid any closure of the connection and to avoid to expire the delays. Then we performed some preliminary tests to have an idea of what is the maximum byte size that we can transfer over the tunnel. And to do this, we have used some dedicated hardware to perform a continuous sending of SMSs within a fixed time window of 60 seconds. Our tests are based on 80 commands that are short text strings that are useful to handle the SMS exchange with the dedicated hardware. We considered to test a scenario, the first where we use the same mobile operator for both the endpoints, and the second where we use different operators. Also, we have made some assumptions about the delays of our tunnel according to the notation of the model that we have developed. We set T alpha to 0 seconds because it is negligible with respect to other delays. TC we considered it to 30 seconds because it is a typical timeout of a browser. And the TS is maybe potentially infinite because we consider that all the tunnel receiver part in our attack is under the complete control of the attacker. And even if it would not be so, typically web server timeout is much more higher than the client timeout, so it can be disregardable too. So to have a feasible tunnel, we just consider the first left part in our previous equation, and we assess that we can have a feasible tunnel if the total amount of time for a complete cycle of request and response is within the client timeout. With these premises, we have obtained some preliminary results, and we first computed for both the test cases the number of SMSs that we are able to send in our fixed 60 seconds. And then with some further mathematics, we have computed the total byte size that we can transfer over the tunnel in the 2 test cases. And as you can see from the results, it seems that by using different operators, we can have a slightly better performance of the system. So in general, despite the short length of SMSs, we have obtained promising results. So it is in the scope of our future work to investigate more on what are the application of our tunnel and what are the limitations, because, for example, we expect that transferring an entire YouTube stream through our system is not so easy. In addition, we will compare our system with other kind of traffics, such as emails or WhatsApp. And finally, we will also work on the optimization of the SMS structure, also to achieve always better performance. Thanks a lot for your attention.
Thank you, Sara. Any question? No. I have a quick one. So if I understood your work, what you are trying to do here is to see if you can implement TLS connection using SMS. Did I understand the aim of the work?
Yes, here this is a preliminary work on this topic, and our goal was to have an idea, above all, if such a system works, and with our while we developed the software code of our system, we have noticed that it actually works. But our idea is, yes, to convey HTTP or HTTPS data through our system in form of SMSs, but we'll we have in the scope of future works also to study the behavior on other kind of data, for example.
Okay. Okay. So
Image
this is
or, okay.
This is what you mean for Covert channel. Okay. Okay. Any other question? Let me check the Slack. And no. So thank you for your work. And
Thank you.
Thanks. I think we can pass to the next and the last paper in terms of ordering, of course. The presenter will be Vincenzo Dentamaro, and they will present a paper, Ensemble Consensus, an unsupervised algorithm for anomaly detection in network security data. So, Vincenzo, 15 minutes. We can hear you, we can see it, so please go ahead.
Okay, welcome everyone, and I'm going to present this paper called Ensemble Consensus. By the way, I'm a PhD student at the second year of from University of Bari, and I'm more in pattern recognition specialization. But this is and it was an interesting opportunity to test our algorithm on traffic data, and that's what we did together with Convertini, Dr. Convertini, Dr. Galantucci, Giglio in Padova, Professor in Padova, Dr. Palmisano, and Professor Pirlo. So in general, so for unsupervised anomaly detection, there are three famous approaches to detect anomalies, and they are based usually on density, distance, and isolation. Within the Ensemble Consensus algorithm that I'm going to present, those three anomaly detection techniques are fused together. Each technique belongs to one of the three fundamental approaches that are mentioned here. So the goal, the objective, is to reduce the number of false positives generated by using an ensemble of unsupervised anomaly detection techniques. So this is the picture of the graph of the process. We have the data collection, then the data is pre-processed to remove the data that is not numerical, and then this data goes within the Ensemble Consensus, which is made by the elliptic envelope anomaly detection algorithm, as well as the local outlier factor and the isolation force, and then all are merged with the it's written majority voting. The truth is that it's not a real majority voting because it was very trivial. And then there is the result. So the algorithm performs this kind of weighted majority voting between three different techniques on the same data, making use of it's called the weighted bagging approach. Okay, so at the core there are those three detection algorithms: the elliptic envelope, which exploits the concept of density, as I was saying before, density. It creates an imaginary elliptical area around a given data set. And the values, so the instances that fall within the area, are considered normal data. Instead, anything that is outside this area is considered, as outlier. The isolation force works in a similar way, but it randomly selects elements, and then randomly it's based on trees. Okay, so it can create vertical and horizontal and vertical lines in order to separate the data sets, and finding what is understood as normal, and so non-outlier, and what is anomaly. And the local outlier factor instead exploits the concept of distance, because it's very similar to k-nearest neighbor algorithm. And in this way, it defines anomalous tuples. So the majority vote, the voting is the main criteria in the Ensemble Consensus. There are two kinds of voting that could be selected. One is the hard consensus. The hard consensus, for the hard consensus, the judgment of the outlier is made based on the score calculated on each technique. At the end, the tuple is classified as outlier by the hard consensus only if at least 2 of the 3 algorithms deem it to be outlier. Instead, for the soft consensus, the average value of the normalized score is between -1 and 1. And this, if the score is over a certain threshold that is defined, I will explain you, then it's if it's over, it's normal. If it's below this threshold, then is classified as anomalous. The Theta Threshold, that is the name that we put on this threshold, is found via grid search techniques. And we think that it depends on the data set used. By the way, after the submission of the paper, we continued doing other tests, and we found that theta put at 0.5, that is the value of that we found with the grid search, it's even, you know, cross data set. So we tested it on several different data sets, and we found out that that threshold is good even for other data sets. But this is something that's not written in the paper because it happened later. So the data set that we use in the paper, it's the KDD99, which is a data set that simulates intrusion in a military network environment. It has 5 output classes. The data set is strongly unbalanced. It has 41 features and 5 billion rows. So the tests that we performed were mainly 2. The test with a large number of data, which is 60, 20, 20. So 60% of the data for training, 20 for validation, 20 for testing. Or we used 5% only of the data for training and the rest for validation and testing. And this is very borderline test, very interesting results. And the tests were also run on tenfold cross-validation. We compared the results with other techniques as well, such as random forest, which are supervised techniques like random forest, Bernoulli naive Bayes, and multi-layer perceptron or feed-forward neural networks. So these are the results. We can see that for the normal, and I mean, for this is the normal test, I mean, where the 60% of the data was used for training and 20 for validation and testing, we see that we have a F1 score of 0.86. Instead, all the other supervised algorithms are 0.91, 95, and so on. So it's not the best, but recall that this is an unsupervised learning technique. And when doing the borderline, so the borderline test, we have a F1 score, which is very low, but the precision is good. Yeah, this is very limited, but it seems that something is it's learning, even though we provided just the 5% of the whole data as training. This result is encourages and suggests that the algorithm can be used effectively also when low quantity of data is present, and can leverage the presence of fresh data. So I mean, this can be designed in an online learning fashion. That's because even though it has at the beginning a small amount of data to understand if the data arriving is anomaly or not, it will, you know, improve its accuracy when more data is received. So I mean, in an online learning fashion, it could be used. So the Ensemble Consensus is able to stand comparison with supervised algorithms, providing a small decrease of score the advantage of working without labeling data. An important result is the recall value, which is not very lower with respect to the supervised algorithm. In future, the system improvement will be for increased recall without penalizing precision and automatically finding the data soft threshold with respect to all the other data sets. And that's what we did and what I explained to you previously. Thank you.
Thank you, Vincenzo. And good, we have a question this time, so I can keep my nasty one for myself. And Tommaso Zoppi has this question. So how are the soft consensus impact false positive and false negatives? I imagine that hard consensus will lower the false positive but makes false negative very high, and this vice versa for soft. So can you please elaborate a bit more on this?
So the question is about not the threshold, but I need to understand more of the question about.
So essentially, the impact of hard and soft on false positive and false negative, because this seems to be hard as an impact on false positive rather than false negative, and soft consensus the opposite. So essentially, they seem to act on the first one on false positive, the other one on false negative. So if you can elaborate.
No, yeah, I understand. The truth is that when we do simple majority voting with the hard consensus, we are not weighting that much, how much we are scoring for each algorithm. So we tested the hard consensus, but we got bad results, okay, on the KDD99. Instead, with the soft consensus, with the soft thresholding, we were able to modify the threshold. And by the way, it's the same threshold for all the algorithms. So the isolation forest, the local outlier factor, and so on. And we find out that using a soft threshold, we could in some way balance between the precision and the recall. Okay, so I mean, I think this is the right answer. The F1 score is weighted with respect to the precision and recall. That's why when we use the 5% only of the data, we got 0.57% of 0.57 of F1 score, because there is a lot of skewness in the data. I mean, there is a lot of unbalance. And to manage the precision and recall, there is this soft thresholding. That's why we produce this thresholding.
Okay. Other questions? We have a time. I'll ask you one. I mean, I have no clue. I don't know anything about machine learning, but you know a bit about networking. And I mean, you use this KDD99. Now, it's called 99 because it goes back to 1999. And it might be, might be a good data set at the time, but it's more than 20 years old. So not very representative of what is the traffic nowadays, because 99 not even existed something like TLS. So did you manage to find anything more up to date?
Absolutely. Absolutely, yes. In fact, we tested it on another data set, which is from 2017, which is the same lablet, because we need to compare it. The idea here was to compare this kind of algorithm with respect to supervised learning algorithm. So algorithm that learns from lablet data. And in fact, we find out that this technique could be used in unsupervised fashion, because data that arrives from network is unsupervised. There is no human being, labeling the data. So we cannot spend years or days labeling automatically data, or in this case of the KDD99, it's simulated data. Instead, we found another data set from 2017 that is always labeled. It's smaller with respect to the KDD99, and the accuracies were higher, the same, about 86, 87 or F1 score. So practically the same.
So you're saying that the time doesn't count. So you worked also with the modern.
Yeah, 2017. It's modern. I think it's all the same simulated. It is because it's, you know, if you want to
so
make
it's not
more,
traffic.
it's not real traffic. It's not
Okay.
real traffic.
Okay.
I have to search to tell you the name of this data set.
Okay, thank you very much. And with this one, we close this session, and I think in time. And next one, okay, next one won't be one, but there are several sessions now that start at 12. So I leave the floor to the new host, and thanks all of you, and see you around.
Okay, thank you.
Okay.
Thank you, everyone. Thank you, Bruno. Sorry, Vincenzo, I interrupted you.
No, I was saying just thank you to all.
Okay, so to all attendees, I'm going to close this session. If you want to follow the other session, you can find the links on the ITASEC website.
Thank you.
Thank you, everyone. Have a good day.
Thanks.
Thank you. Bye.
Bye-bye.